to my project phase 3 presentations. I'm using a time series of a stock price as my data sets. So for this presentation, I'm using Amazon's 5 years hourly historical stock price as the data set. So first of all, I simply just plotted the weighted average price for Amazon, and I see the distribution of its price doesn't mean anything, and I run a Fuller's test on the average price. That p-value is bigger than 0.05. That indicates the data set itself is indeed non-stationary, and that's why the distribution of the data of the price is meaningless. So I attempted to run a stationary process with the raw data to see if there's any improvements. So the way I perform this stationary process is take the log of the price points and I shift or I differentiate the price point with a shifting window of 35 data points. So I'm using 35 because there's a 7 trading hours a day and 5 days a week. So I shift it with a window of 35 and I plotted the the data points, and now it looks somewhat normally distributed. Well, I care about the data set distribution because I'm hoping to see the data or the time series is strongly self influenced by time. Over the time. So I run Fuller's test again out on the stationary processed price, and this time the p-value is significantly small. It indicates now the data set or the time series is stationary. However, even though the data set itself looks normally distributed, I still run a normality test with a SW test. So the p-value of this test is 5 point something times 10 to the negative 42. That indicates the data set or the time series is not normally distributed because less than 0.05 rejects my null hypothesis, which is the data set should be normally distributed. However, I still want to extract some useful informations or features from the data itself, so I use autoregressive approach. So autoregressive approach is often used in time series analysis. So I simply just plot the autocorrelations of the weighted average price of this time series. I find out that above 3,000 or around 3,000 observations in this time lag usually means observations. In 3,000 observations, the autocorrelation is above 0 or positive. That means autoregressive should work if the forecasting period is around 3,000 data points. So I built an autoregressive model using some stat model package, and I built a autoregressive model with a order of 7. 7 means, like I said, there's 7 hours trading each day, so I'm using a sliding window or a moving average as one day. And there's one non-seasonal stationary process during training this model. That means each data point would have a stationary correlation or stationary. Each data point and its previous data point should have no seasonal characteristics, and that means pretty much means it's a random walk, and there's zero lag error as the model learns the dataset. Well, I use zero because I said I'm doing a random walk approach, so I should not learn any previous sliding windows or predicting result as a influencer to my pair outcomes. So the model detail is shown below, and as you see, as of the order goes up, like the sliding window increases, the p-value drops. So the point I'm caring about the p-value is without confirming the p-value is in a significant range, which is 0.05, I cannot assume or I cannot suggest the model would work in the future. So I plotted the residual error of this model again, just double check. As you see, there's no uptrend or downtrend, just a lot of spikes. That indicates the data set or the model itself it is stationary, but is influenced by seasonal data, because I'm using one, basically it's a random walk. However, before I start training my model, I noticed that if at shifting window 4 or order of 4, the p-value has a cut. It cuts from 0.551 or 0.3 to 0.005, which is less than 0.05, and then it goes up to 0.2. So I think I should use order of 4 instead of 7 to increase my outcome. So I trained the model again with order of 4 and just a random walk, and I still produce a p-value at 0.004 at a sliding window 4 or a moving average of 4. So the result is, well, like I said, because after I plotted the autocorrelation plots, I noticed that the useful predict window of this model would be just 3,000 data points. So I chopped the data set into 60% and 30%, 66% and 34%, 66% as the training set, and 34% as a test set. In addition, the data set itself has around 8,700 data points, so that makes sense. The test set is roughly about 3,000. And as you see, the result is quite promising or acceptable because first of all I plotted the actual price point of the test set against the predicted price point with the test set, and as you see, the trend line is pretty close to each other. And then I double checked it with a mean squared error, and it is 91.61. So consider that has 3,000 data points. That means the average mean squared error for each data point is roughly about 0.03, means has a 3% error, which is, 3% mean squared error. That is pretty impressive just using the data itself. So I read more stuff about stock price analysis, and I realized there's actually more data or more information could be extracted from the data set itself. So I computed the 10 useful indicators to based on the data set itself using the close price this point at this time, because weighted average price, like people said, is weighted. So that might be that might affect the feature importance while computing those features. So I computed a smooth moving average period of 5 and 8, and I also computed a MACD line. That line usually indicates when to buy and sell a stock. And I also computed a Bollinger's bands. So it's a band this band has an upper bound and lower bound. So usually the stock price would move within the bands. So that actually indicates that sets a movement limit or movement range limit to these models. So I use a XGB boost to try to extract the feature importance. With these new features, I'm using a squared error as a regressors, indicators, or evaluations, using roughly 200 estimators. The reason I use 200 is I try to build I try to build 20 trees with each dataset, each features as a roots, and the depth is about 10. That is each, because there's 10 features, so I'm trying to build a depth that goes only 10. And the learning rate is 0.05. It's pretty standard, and I actually increased the lambda, or the regression lambda is a L2 regulators that try to produce a more conservative models that could be useful later, because I don't want this model to be too random, or I don't want the feature importance randomly being influenced by something else. So I plotted the feature importance. As you see, that the smooth moving average 5 and the Bollinger's band, the momentum, and the EMA 12 is pretty significant. So I decided to use them as a feature to train my LSTM model alongside with my autoregressive outcomes. The reason I don't have the LSTM is because the dataset is too long or it's too big, so I run into a hardware